So this is going to be a problem about comparing multiple means. If we only had two means, and by that I mean we have a continuous numerical variable or a variable with a numerical level of measurement. Let's make it a ratio type. And we have another variable that is binary, so categorical with two categories. So I can completely split my data in two. So I have this numerical variable and I have two groups that I form from this binary variable. Then I can use a t-test to compare the two means of that single variable. But imagine the categorical variable, the nominal variable that divides my data set, has more than two categories. Maybe it has three categories, as we'll see in this problem. Then what do I do then? I cannot use a t-test because a t-test is just about comparing two means. Now I want to compare more than two means. And what we do is we just generate a linear regression model. And we're going to see our numerical variable, remember, as our response variable. It's continuous response variable. And our explanatory variable is now going to be this nominal variable. In the problem that we have today, it's going to have three categories. And that means we're going to have three means. So let's have a look at the problem. It reads, researchers investigate lung function capacity by measuring the forced expiratory volume in the first second to the forced vital capacity ratio, and we abbreviate that by FEV1 over the FVC. It's a measure of how well your lungs are performing. They claim that this ratio is different among healthy volunteers, that's the control group, and similarly aged individuals who smoke substance A and individuals who smoke substance B. So you can clearly see there the nominal variable, and we're going to have a set of subjects, and some of them will be control, some of them will be substance A, and some of them will be substance B. So we have a nominal variable with three categories. And so when we look at this numerical variable, this FEV1 over the FVC, that's going to be a continuous numerical variable, and we're going to have three means that we have to compare to each other. So they measure the ratio in 100 randomly selected subjects in each of the three groups. So we're going to have 300 subjects, 100 in each of these groups. And so you can imagine a spreadsheet with 300 rows of data, and with the two columns, one with our numerical variable, one with our categorical variable. And so the results are summarized in the table below. We see a total number of subjects of 300, 100 in each group. We see a mean of this FEV1 FVC ratio in the control group is 81.299. That's the sample mean. For substance A group, that's 76.492. And for substance B group, that's 78.585. And then we see our intercept estimate. Remember, that's beta sub 0 hat, 81.299. And we immediately notice that that is exactly the mean of the control group. Then we see the standard error for that, 0.604, the coefficient estimate for substance A group. And look at that, it's negative 4.807. And if I take the intercept, that is 81.299, and I subtract 4.807, I get to 76.492. That'll be the mean for the group A. And that's how this model works if my explanatory variable is categorical. So we see all the coefficient estimates there, and we see the standard errors. Then we have a sum of squares total. So for this kind of model, we can still work out a sum of squared errors. So we see the total there, 1,000, that should be 11,996. We see the SSR, the sum of squares due to the regression, and that's 1161.759. And the SSE, 10,834.409. And we remember that if we add the SSE and the SSR, we're going to get to the sum of squares total. So the researchers choose the control group as the reference group, as we surmise from the summary that we were given. Look at that. The intercept is exactly the same as the value for the mean in the control group. So test their claim, and their claim would be that there's a difference in this ratio amongst these three groups, but by looking at the following questions. Use a 5% level of significance throughout and assume that the assumptions for the use of parametric tests are met throughout. So in question number 1, test the claim of the researchers that the mean FEV1 FVC ratio is different between the healthy controls and those who smoke substance A and those who smoke substance B. And the hint there is to use an F-test. And that's exactly what analysis of variance is. And that's why you have some textbooks with a totally separate chapter for calling analysis of variance a test for the difference between more than two means. Question number 2 is determine and interpret the coefficient of determination for the model in question 1. Note, if you reject the null hypothesis in question 2, then proceed to the rest of the questions. Question number 3 is, how many pairwise comparisons can be made? That is what we do if and only if we reject the null hypothesis of our F-test. Otherwise, we don't go ahead and we don't do post-hoc analysis. Calculate the adjusted level of significance using the Bonferroni correction, and perform post-hoc analysis to compare the mean FEV1 FVC ratio in healthy volunteers, compare that to the mean ratio in those who smoke substance B. So we only need to do one of those because, question number 1, how many can you do? And it takes a long time to get all these done. So let's get started. So I've got the summary here for comparing three means. We've got the overall number of subjects, 300, 100 in each. We see the three means, and we do immediately notice because we chose this control group, which I'm going to use X sub 1 for that control group. X sub 2 is my random variable for the substance A group, and X sub 3 then for the substance B group. And because we chose this first group, our control group, as the control or the reference group in our model, we're going to see that beta sub 0 had the intercept that is exactly the same as that mean. And if I take 81.2998 and I add to this negative 4.8070, in other words, I'm subtracting 4.807, I'm going to get exactly 76. And if I take 81.299 and I add to that negative 2 or subtract 2.7137, I get 78.585. And that is what happens with a linear regression model if I have a single categorical variable as my explanatory variable. That's exactly what's going to happen. We see our standard errors there, the SST, SSR, and SSE. So let's start with step number 0. And step number 0, I'm going to write it down. You don't have to, because we've already got our summary. Everything is summarized for us right there. So let's look at step number 1. Now step number 1 is what population parameters do we have? And we can say that we can look at it in a different way. We can look at these three means. That's going to be mu sub 1, mu sub 2, and mu sub 3. Remember, we use mu because we're talking about population values here, so that's parameters. And this one is going to be the FEV1 over FVC ratio in the healthy population. And by healthy here, I think we just define the problem to say that these are people who don't smoke, and definitely not substance A or substance B. So I'm going to be lazy but today, and so let's just put little marks here to show that I'm just copying the line above. So mu sub 2 is then going to be the FEV1 forced expiratory volume. So that's when you inhale as much as you can, and then you force that volume out as much as you can, and the machines are going to measure in that first second what volume you actually exhale. And then the forced vital capacity is you exhale as far as you can, and that's the total volume. There'll always be a residual volume that you cannot get out because your ribcage can't collapse completely, expelling all the air. And anyway, mu 2 would be those who smoke substance A, mu sub 3 in the population who smoke substance B. Notice that we can also use beta sub 0 and beta sub 1 and beta sub 2. And these are going to be the intercept and the two slopes, saying on average how much does this mean change for comparing this group to that group, and this one comparing this group to that group. So we can look at it in any way, but it makes sense here to use the means. Just want to show, I mean, it's exactly the same whether you use the means or whether you use these, the intercept and the slopes. You get exactly those three values. They're telling you the same thing. So in step number 2, is we want to write the null and alternative hypothesis. So let's put the null hypothesis just all means are equal. And in our alternative hypothesis, not all means are equal. Okay, so we're not saying if it's mu1 that's different from mu2, or mu1 from mu3, or mu2 from mu3, or they're all different from each other. It's just they're just not, there's a difference. At least one of them is different from the other two. And so when we look at the coefficients, then we would say beta sub 1 and beta sub 2 are equal to 0. Okay, let's look at step number 3. And that says what is our chosen alpha value, our level of significance. The problem told us to use a 5% level of significance. Step number 4, what test are we going to use? Well, we're going to use an F ratio test. And we were told that all the assumptions for the use of a parametric test such as this are met. And remember, by this we do mean that we're using analysis of variance. Let's do step number 5. Step number 5 is we have to work out what this F statistic is. So let's do that. We just want to remember, let's put that in green. We want to remember how we're going to calculate this. F is going to be this ratio, and it's going to be the SSR, and that is going to be divided by nu sub 1, our numerator degree of freedom, divided by SSE, the sum of squares due to the error or the residual, divided by nu sub 2. Let's get a ruler out. Let's just put some nice lines down. I should put a longer one there because that is my whole numerator and that's my denominator. And this is going to be described by, it follows the F distribution on these two parameters, nu sub 1 and nu sub 2, numerator denominator degrees of freedom, under the null hypothesis. If the null hypothesis was true, then this is the distribution of F values that I should get. And now we just have to work out what nu sub 1 and nu sub 2 is. There's a little bit of space, let's do it there. Nu sub 1, that is going to be k minus 1. Now, please do remember, different textbooks do it differently. I like to define k as the number of parameters in my model. And how many parameters are in my model? 1, 2, 3 parameters in my model. And 3 minus 1 is 2, so my numerator degree of freedom is going to be 2. Let's do this one. Remember, that's n minus k, and that's my total number of observations. So if we look at ours, we're going to have that nu sub 1 is going to be 2, and nu sub 2, 300 minus 3, is going to be 297. So we are going to have to plug that in, 2 and 297 degrees of freedom. So let's work out what our F ratio is. So let's just put it there. Our F is going to be described by the F distribution in 2 and 297 degrees of freedom under the null hypothesis. And let's work out what ours is. So we're going to have to plug in these values. Let's see what they were. So that's going to be 1161.759. That's going to be divided by 2. And then for the SSE, it's going to be 10,834.409, and that's going to be divided by 297. So let's have a look at this. Let's put parentheses. We're going to say 1161.759. We're going to divide that by 2. Let's move outside of that set of parentheses, divide by another set of parentheses. That's going to be 10,834.409, and we're going to divide that by 297, and let's see what we get, 15.923. So let's do that. F equals 15.923. So in step number 6, we're going to do our decision rule. So let's do a critical value. We're going to do a critical value, and remember our alpha is going to be 0.05. So when we look at this curve, let's draw the curve. So this is just a very rough curve. I'll have to use software to look at exactly what the curve looks like with the two parameters, 2 and 297. Imagine it looks something like this. We want to move all the way across till we get to some critical value. Remember, these are all f values. That'll be our critical value there, such that on this side we have 95% of the area under the curve, and this is the least probable on this region here, the least probable, or the 5% least probable values, and that is going to be our region of rejection. So let's have a look at that. Now we do use the numworks calculator, which runs into a little bit of an error in my experimentation. You'll have to see yours. I'm using a HP prime calculator here, and the critical value, let's put it down, the critical value for me, and if that happens in any kind of exam, I will always, for all students, I will give you this value. If I find that the calculator that we do use runs into a bit of problems, 3.026. And that's my critical value. Let's put a little c there as a subscript. Let's do that. And so we have that our F statistic is larger than the critical value, and hence we're going to reject the null hypothesis, and we're going to accept the alternative hypothesis. And so in that was step number 6. In step number 7, we're going to write our conclusion. So I've just written there's enough evidence in the data at the 5% level of significance to show that the FEV1 FVC ratio is different between healthy subjects, those who smoke substance A and those who smoke substance B. So we are actually saying if the null hypothesis was true, if the three means were equal, imagine that's the population, and I do the study repeatedly, taking 100 from each at random, I'm going to get a bunch of F values, and this is how the F values are going to be distributed. And these here in the zone of rejection, that'll be the 5%, the region that contains the 5% least probable F values, and hence I'm happy to make that error, that type 1 error, and I reject my null hypothesis. Even though, remember, this curve is about the null hypothesis being true. Given that all these F values, even way out here, they are all true and possible, we just decide that we're going to reject them. So before we go into darkness here, let's just look at the second part. We're going to do post-hoc analysis. And remember, for the post-hoc analysis, how many can we do? Well, for 3 groups, we can say mu sub 1 and mu sub 2. We can say mu sub 1 and mu sub 3, and mu sub 2 and mu sub 3. So we can do 3 of these analysis, post-hoc analysis. So we're going to have a new alpha value, but the Bonferroni correction, because we don't want to add, we keep on adding to this 5% if we do these comparisons. And so we're going to say this divided by how many post-hoc or how many pairwise analysis can we do, and that's 3, so 0.05 divided by 3, that's going to equal 0.0167, 6 just repeating. And so for step number 0, we know that we have all the results that we already need. For step number 1, I think we were asked just for this one, but remember you'll have to do three of these. And so we're going to say mu sub 1 and mu sub 3, that is the FEV1, FVC ratio. So that's going to be this mean of this value in healthy volunteers, the mean of this value in those who smoke substance B. In step number 2, we want the null and alternative hypothesis. The null hypothesis here is mu sub 1 minus mu sub 3 equals 0. In other words, if I just take this over to the other side, that those two are equal to each other, the alternative hypothesis is that it's not equal to 0, so we're doing a two-tailed alternative hypothesis. Step number 3, we were told to use an alpha value of 0.05, but remember we do the Bonferroni correction, so that is the new alpha value. Step number 4, what test are we going to use? We're going to do a t-test. In step number 5, let's look at what this equation looks like. So remember, we're going to go for a t-statistic, and that is going to be x bar in our instance. I'm going to put I and j just to show you that these are 2 different groups. In our instance, this is going to be 1 and 3. Remember, we do subtract this because we needn't set that. In more advanced courses, you'll learn you don't need to set that equal to 0. So we're just going to say mu for the first group minus mu for the second group. And so that's going to be minus 0 because we use 0 there. And we're going to divide all of that by the square root, and that's going to be the SSE. So this is going to be this within group variance in some textbooks. This is going to be n minus k, and then we multiply that by 1 over n in the first group plus 1 over n in the second group. And that's going to be distributed by the t distribution, and the parameter is going to be nu under the null hypothesis. And we just have to work out what nu is in our instance here. That is going to be n minus k. So let's do the substitution and let's have a look. Just here for us, remember nu is going to be 300 minus, it says this k here means how many groups do I have? I've got 3 groups, and that is 297. That's fine. And let's plug in these two means. So that's going to be 81.2998 minus 78.585. Great. Divide by this square root. Let's do the SSE was 10,834.409, and divide that by 297. And you're going to have 1 over 100 plus 1 over 100. There we go. T equals, let's just do this one as well. There we go. It looks better. It's going to move up the paper because we're really getting shadows today. And let's do that calculation. Check on your calculator. I get 3.178. And step number 6, we have to do our critical value approach. So we have to calculate T crit. And remember, that has got to be on this 297 degrees of freedom, and we have a two-tailed alternative hypothesis, and we also have to remember that we use 0.0167 as our alpha value, and you can have a look at that and on the numworks calculator, and that works out to 2.408 for me, and we can see that our t value, and we're going to use the absolute value of that to always make that positive, that is going to be larger than our critical value, and we reject the null hypothesis, and we reject the null, and we accept the alternative hypothesis. Let's do step number 7, where we're just going to use a test conclusion. So let's just try and move that up so you can see there's enough evidence in the data at the 5% level of significance to show that the mean FEV1 FVC ratio is different among the population of healthy volunteers and those who smoke substance B. Remember, that's always in the population. And so that's how you do comparing more than 3 means. And remember, this is just a linear regression model, and we use those 2 dummy variables. In other words, we use the categorical variable as our predictor variable, our explanatory variable, and we use the numerical variable as our response variable.